Every crew gets to design their own patch. In this next scene here, you'll see our patch, which has the entire globe as well as the sun on it, symbolizing the global nature of looking at atmospheric research and the effect the sun has on the chemistry of our atmosphere. We had the opportunity to launch midday on November 3rd, which made it a very comfortable wake-up for half of our crew, waking up at 7 o'clock in the morning. However, because we were a dual shift flight and conducted operations around the clock, the other 3 members of the crew had sleep shifted themselves to wake up at 10 o'clock the previous evening. So they'd been awake about 12 hours, or actually 14 hours before we launched. We check the integrity of our suits, and then we walk out of the ONC building at the Cape to get on the Astrovan for the 7-mile drive out to the pad.
We had a beautiful morning for the launch. The skies were crystal clear, not a cloud in sight. At T-minus 6 seconds, the shuttle main engine start sequence began, and moments later we're on our way. The 66th mission of the Space Shuttle program and the 13th mission of Space Shuttle Atlantis. We were already over 100 miles an hour as we cleared the tower, and we began our roll maneuver to the attitude required for our 57-degree high inclination orbit. Our trajectory actually took us up the eastern seaboard of the United States, just off the coast. At this time, the orbiter, at liftoff, the orbiter weighed around 4 million pounds, and our thrust was around 7 million pounds, so the thrust to weight was pretty nice, and we were getting out of town in quite a hurry, as you can see. The orbiter was burning about 3,000 pounds of fuel per second, and as that weight decreased, the acceleration increased up to about 3 Gs, or 3 times the Earth's gravity. At 2 minutes into the flight, we had expended all the energy out of the solid rocket boosters, so they were jettisoned to be picked up by the recovery ships waiting about 50 miles off the Kennedy coast. It's hard to imagine we sit on the pad, and then just a few moments later, we were at orbital speed, just under 18,000 miles an hour, and we did all that in 8 minutes and 42 seconds. So you can imagine the ride and the acceleration was quite unbelievable.
At main engine cutoff, we went from 3 Gs to almost 0 G instantaneously. It was quite a spectacular sensation. My first job was to film the external tank, which was flying in close formation with us for post-flight analysis before it re-entered the Earth's atmosphere.
And one of the first things we do when we get to orbit is open the payload bay doors, and we do that for thermal reasons, but it's also a pretty exciting event for the crew because it gives us our first real view of the Earth from space.
The first day was very busy with activation of all the payloads, including the CRISTA SPA. You see Kurt and Joe in the forward flight deck controlling the digital autopilot and also keeping the big picture of on all the systems. While on the aft flight deck, Ellen is flying the robot arm to grapple the CRISTA SPA with a special electrical connector to activate the batteries. You see the arm closing to the payload. You can see the target, which is a very important visual cue for the arm operator to center the end effector and the snares around the grapple fixture. Then comes time for the deploy, and starting with the unberth of the payload very smoothly to prevent any saturation of the gyros on board the CRISTA SPA, and then a maneuver from the low hover to the release attitude. You can see the mass antenna moving, scanning the atmosphere. It is quite a long maneuver from the low hover to release attitude. CRISTA SPA is a composition of the platform SPA and the instrument CRISTA and MARCI. CRISTA stands for Cryogenic Infrared Spectrometers and Telescope for the Atmosphere. And with the 3 telescopes on board and very high-speed sensors, it collects a very high space resolution data of the middle atmosphere. And when we get ready on the orbital side as well as on CRISTA for release, I check the trigger to open the snares in order to start the release. And you can see now the end effector backing away from the payload. Very nice view of the Earth in the background. And when the arm stops at a few feet from the payload, Don from the aft flight deck will fire the first separation maneuver. And once the deploy is complete, the ground team and the crew on board is very happy with the successful deploy.
Here's a view of the payload bay showing the atmospheric and solar science instruments. The main structure that you see is the Space Lab pallet with the 6 Atlas instruments on board, as well as a lot of the support equipment. This is a close-up of some of the solar instruments, and you see the door opening on SolCon, which measures the amount of energy coming from the sun. And this is another view of the payload bay taken from the camera that's on the elbow joint of the robotic arm. Here's a view of SSBUV, an ozone measuring instrument, as the door opens and it begins to measure the backscattered ultraviolet light from the Earth, which will allow it to measure ozone.
This is the ESCAPE payload, a solar physics experiment sponsored by the University of Colorado, and it took advantage of 4 solar viewing periods throughout the flight.
This is the assembly of one of the biggest secondary payload in the mid-deck heat pipe performance experiment, dedicated to testing heat pipes extensively used on board automatic satellites to cool electronics. Hélène is currently running a spin test where pipes are spinning to see how centrifugal force prevents the heat pipe to work properly, and we could set the power as well as the spin rate. We had also a PGAC to help collecting data.
This is the protein crystal growth experiment. We had 2 on board, and we've been told that we had the highest yield and some of the highest quality protein crystals they've ever seen since protein crystal growth experiments have flown on shuttle. And the crystals will ultimately be used to determine their 3-dimensional structure and ultimately lead to better pharmaceutical development. And this is a close-up of one of the chambers showing some beautiful, very large protein crystals.
3 gold boxes that you'll see in the frame here on the locker doors were the accelerometers for the Shuttle Acceleration Monitoring System, SAMS, and we used that equipment to document the microgravity environment on the orbiter.
This is a piece of equipment called Albert that Jean-Francois and I used to position ourselves when we were operating the robotic arm for the deploy and the retrieve.
Our galley was the focal point of life on orbit. We hydrate some of our food with hot or cold water as indicated on the package. Then we cut the package open and eat the food with a spoon. Even after all those years of being told not to play with your food, when eating in space, it's almost too much fun to resist. Jean-Francois invented a new dish, shrimp cocktail on a tortilla. I think building the shrimp fajita was half the fun. Of course, eating it was pretty good too.
We had plenty of cameras on board to document not only our in-cabin activities, but also the extensive Earth obs potential we had on our 57-degree inclination flight. We took over 6,000 frames of film on our 11-day mission, and it's a great opportunity to see the world without boundaries, and also to get a better feel for meteorology, oceanography, and geology. And this is a tremendous view of plate tectonics in action. This is the Indian plate meeting Asia, arising in the Himalaya range. And in the foreground, you can see the Ganges River here, several of its tributaries and alluvial fans that feed into the Ganges, and the foothills to the Himalaya range. And this is literally the roof of the world. There are several 8,000-meter peaks in this field of view here, including Mount Everest and Annapurna. Just a gorgeous sight that the Blue Shift had a chance to see on several passes. Up at the top of the field here is Bow Tie Lake, one of the landmarks that we use to identify Mount Everest as we go by. And now in the field is the Tibetan highland. It's a very arid land with a mean altitude of 14,000 feet above sea level.
This is a beautiful scene of the Great Barrier Reef off the northeast coast of Australia. You can see the coral formations, the different color water indicating different depths, several plankton blooms, and the ocean currents in the sun glint to the right.
We had the opportunity to see several major storms while we were on orbit. This one was Hurricane Florence that occurred early in our flight. We had the opportunity to pass by and zoom in on the eye of the hurricane, and you can see a very well-defined wall.
We had the opportunity to exercise almost every day on orbit, and here you can see Jean-Francois enjoying the exercise, the music, and the view. It was pretty spectacular to do that. This is a view of the inner limb resistance device, an exercise device that I developed when I was out at Ames with one of my colleagues there. And it allows us to exercise all of our anti-gravity muscles while we're in space with minimal impact to the orbiter. In addition, it allows us to preserve some of our neuromuscular coordination when we return back home We can also reconfigure for upper body exercises.
During our half-day off, we had a chance to play with zero gravity, and perhaps my drill instructor from officer school would be impressed with this maneuver.
Another big challenge during our little free time on orbit was with Scott and I trying to rendezvous two big bubbles of water together, and we managed to do that, although it's very difficult to handle this soft big bubble in the middeck. And even when you want to take a CD, you know, it flies away like a frisbee.
This is me being attacked by the morning mail messages from Mission Control one day.
We are frequently asked how we sleep in space, and though on different shifts, here the three rookies are demonstrating the use of our sleep stations.
We had a peculiar phenomena occur during one of our supply water dumps. We dump water overboard that's either not needed for cooling or consumption by the crew. You can see in the upper left corner here is the supply water dump nozzle with a stream of water coming out. What's building here is an icicle that formed on the outside of the cargo bay door, which is off the picture to the right. And the icicle formed and would have continued formation probably right up to the dump nozzle had we not stopped the dump at about this time. Now watch the plug here. This is a look at the entire icicle after it had formed about 6 feet long off the payload bay door, and that part of that ice remained all the way through the entry until post-landing. It was still on the vehicle.
Here we have the flight deck crew, Don, myself, and Joe preparing to do a procedure called flight control checkout, where we crank up one of the auxiliary power units for hydraulics, and we move all the flight controls and check all the instrumentation and displays out for our trip home, make sure Atlantis is ready to come home. Standard procedure we do every mission.
And after 8 days of free flight, it was time to join back up with spas to bring it home. It is a beautiful sight here against the deep black of space. Kurt monitored the rendezvous and performed the final burns from the left seat, while I managed the various sensors used to display our approach on a portable computer. Don flew the final stages from the aft station, taking inputs from us and the computer program, but ultimately using the best sensors we had on board, his very own eyes. We worked our way in until we could see every detail of the surface of the CRISTA spas. Finally, for the grapple, Jean-Francois operated the handheld laser and gave Don and Kurt very accurate range and range rate measurements that allowed us to make our rendezvous time almost down to the second.
Here's a little closer view of CRISTA spas as Don is flying the final part of the approach, and I'm getting ready to use the robotic arm to do the capture. And this is a view of the arm as it's coming in over the grapple pin, and then I initiate the capture sequence, which pulls the payload onto the arm and rigidizes it. Here's a view after we've captured it and before we've berthed it in the payload bay, looking out the overhead windows. And the rendezvous was accomplished on Flight Day 10. On Flight Day 11, we went into our final solar viewing attitude, the last opportunity for the solar instruments to take measurements. And then Flight Day 12 was our day to come home. And this is us preparing to come home. And one of the last things we do is close the payload bay door.
Well, once we have the payload bay doors closed, it's time to reconfigure Atlantis for the trip home. We get back in our orange pumpkin suits and we prepare for the burn. We use our engines to slow the orbiter back down to re-enter the atmosphere. It's time to turn some of that kinetic energy we gained during launch back into heat. And Joe's pointing out the window, so Jean-Francois takes a look, and you can see the plasma behind us as we stream through the atmosphere, converting that energy back into heat. Out my right window here, you can see the glow around the orbiter also as we're penetrating the atmosphere. Don's managing the energy, make sure we have good energy state, and here's the long-range camera from Edwards picking up our yaw jet thrusters still firing to maintain attitude.
This is a look out Kurt's right window there as we make about a 90-degree turn to final at Edwards. As we roll out on final, we had one final test to perform before we landed. It was a subsonic aero test to roll the vehicle left and right and to yaw the vehicle left and right to look at control power in those control surfaces to see if there's a potential for more crosswind capability in the vehicle. Once that was complete, we rolled ourselves back out on final approach. We fly the approach now at about 300 knots equivalent airspeed. At 2,000 feet or so, we begin to decrease our glide angle from 20 degrees to just over 1 degree. At 300 feet, Kurt extended the gear for us, and as we continually decelerate, we cross the threshold of the runway at about 225 knots, 17 feet in the air, and targeting a touchdown speed of 195 knots. We touched down about 3,200 feet down the runway, and immediately after touchdown, we deploy a drag chute. We had the first reusable drag chute of the Space Shuttle program. The drag chute helps us decelerate as well as lowers the slapdown rates on the nose gear. The deceleration we get out of the drag chute reduces the amount of runway we use by about 1,500 to 2,000 feet. At about 60 knots, we release the drag chute so we don't have to contend with that hardware post-wheel stop. And by this time, we had flown about 175 revolutions of the Earth, and we'd been in space almost 11 days and flown 4.5 million miles. And we badly needed a shower and a home-cooked meal.
No shuttle presentation would be complete without a shot of our launch. It's a very exciting beginning to the mission, and this is a view from the base of Pad 39 Bravo at basically sea level, just a few seconds after the orbiter has lifted off. Again, we had a beautiful day that day, crystal clear blue skies. I don't think I've ever seen it any bluer, and it was quite an ascent. A few days later, however, we had another chance to look at Pad 39 Bravo from a different perspective, from about 165 miles directly overhead. And you probably recognize most of the things here in the slide. We have this pad right here is 39 Bravo, where we left off, did our liftoff. And you can see the southern pad and also the crawler track where we maneuvered the orbiter from the vertical assembly building and the orbiter processing facility here out to the pads. The shuttle landing facility is right in here, as we see. And if you take a bigger view, you can see down here the skid strip at Cape Canaveral complex, and also the beginning of our space program, the very historic pads we have here for the Mercury and the Gemini program, along with some of our expendable pads that we use to launch the expendable payloads, or expendable rockets, I should say, into orbit. Cape Canaveral Seaport is down here, and if you come on fine, Cocoa Beach down to Patrick Air Force Base is here, on up through Cocoa, and we have Titusville Airport and Titusville up in here. So it's quite a view, again, very clear for Florida. And this is where we were supposed to land November 14th. Obviously, Tropical Storm Gordon had other plans, so we wound up in Edwards.
Here's another view of our payload bay, and I wanted to point out some of the instruments that we were carrying on board. We had 3 atmospheric instruments, 2 of them on the Atlas pallet, one of them here, Atmos, and then you can see the Maz antenna over here. Then up here on the starboard sill, the SSBUV instrument. All 3 of those instruments measure ozone, and one of the exciting results was to compare the ozone measurements between all 3 instruments, which we were able to do in some of the northern hemisphere measurements. Atmos and SSBUV were also, of course, focusing on the Antarctic ozone hole, which was present during our flight and was just beginning to recover. And they were measuring the ozone within the hole at about half the level of the ozone outside the Antarctic ozone hole. Atmos also measures about 3 dozen other trace molecules in the atmosphere to get a much more complete picture of how the ozone depletion process occurs. It measures chlorine, which is the primary catalyst for ozone depletion, and a lot of the reactive nitrogen species which can bind with chlorine and prevent it from depleting ozone. And we were able to get what the concentrations of those chemicals were as a function of altitude, both within the hole and outside the hole. And they also found that chlorine exists in different reservoir species at different altitudes, which was a new and interesting result for the scientists. Atmos also measured in the mid-latitudes one of the freons, Freon 22, at a value that had doubled over the measurement that it took in 1985. And we really still don't know the significance of what that might be. Some of the solar science instruments, there's 3 solar science instruments in the center of the palette, ACR, SolCon, and SolSpec, and there's one on the far side of the palette that's hidden from view called SUSIM. 2 of those measure the total amount of energy coming from the sun. They were very pleased with their results. They were able to get measurements with a precision of less than 0.05%. The other two measure the solar spectrum as a function of wavelength, and along with SSBUV, three of them independently measured the ultraviolet solar spectrum, which is a difficult measurement to make because ultraviolet light affects the optics of the instruments. So they were very pleased at that result. And the final instrument on board is way in the back, and you can just barely see the door open behind the Atmos. That's the ESCAPE instrument, and it's a solar physics experiment looking at the sun in the extreme ultraviolet wavelength region. This is our other primary payload you've seen in some of the other shots, the CRISTA SPA satellite. And CRISTA is the main instrument that you see here, the big white cylinder, and it's cooled by cryogenic helium, which is what takes up a lot of that space there. CRISTA's primary objective is to understand more about weather in the stratosphere or the middle atmosphere. Of course, we're all familiar with weather in the troposphere, which is what we experience every day. But there are a lot of phenomena that are very similar in the middle atmosphere: winds, turbulence, large temperature changes, and not very much is known about that. And by measuring different chemicals that can act as tracers, they hope to understand quite a bit more about that as they go through their data. They're also producing the first global map of atomic oxygen in our atmosphere, which scientists think help cool the Earth. The other primary instrument, MARCI, is sitting right here under these insulating blankets, and it was measuring hydroxyl and nitric oxide, which are two important chemicals in the ozone depletion process.
We had, as I mentioned, opportunity to see 3 different storms. One of them was super cyclone Zelda that was out in the Pacific. We also saw Tropical Storm Gordon develop off the coast of the Yucatan, which eventually became a hurricane and caused some pretty heavy rains in Florida and severe damage. Gordon was also one of the reasons, obviously, that we did not land at the Kennedy Space Center, because it was affecting the peninsula at that time. This is, again, Hurricane Florence, which developed southeast of Bermuda. It eventually moved north and became extratropical and never reached landfall as a hurricane, but the moisture from this storm combined with a storm over Europe and caused some fairly severe flooding over France and Spain. This is the Indonesia, or part of the Indonesia chain, looking from the north to the south. The large island here of Java is present, as well as the islands of Bali here and Lombok. On Bali and Lombok, there were some fairly severe eruptions of volcanoes in the summer of 1993. There are 2 volcanoes on Java that are venting steam right now. One of them is Arjuno, which is near the center of the screen, and it's difficult to see the venting that's occurring. Also over on the right side of the screen, which is difficult to see here, is Marapai. Marapai, 3 weeks after this photograph was taken, had a major eruption which caused some fairly deadly mudslides to occur on the island of Java.
This is the Ganges River Delta, the largest delta in the world. This photograph is centered on the country of Bangladesh. And what you can see here at the base is massive amounts of silt and clay sediment originating from the Ganges and Brahmaputra rivers far upstream. It's an ecological area of key importance because all of this is mangrove habitat. It's an area where many aquatic and land forms live, notably in the remaining forested mangroves here at the bottom of the view. The Asian tiger resides. Unfortunately, other pressures have caused a significant amount of deforestation and movement towards converting mangroves into rice paddies. And so the shuttle photography helps scientists document the rate of environmental change as well as geologic change, including delta growth because of all the sediments coming from the rivers upstream. This is a gorgeous shot of the highest mountain in the world. This is the summit of Mount Everest. It stands at 8,848 meters, or for those of you who aren't metric, it's 29,000 feet and change. It is an area of special significance for me because had I not been selected as an astronaut 2 years ago, I would have been on a climbing expedition and probably, or hopefully, would have been standing on the summit as my STS-66 compatriots flew overhead. And this is a tremendous synoptic view, a low oblique of the region that we've just been talking about. Off in the distance here, you can see the beginnings of the Ganges River Delta. You can see the foothills of the Himalaya, the roof of the world, and the Tibetan Plateau. In this view, you can see Bowtie Lake, which we pointed out in our movie. You can also see the Everest region and the Annapurna region. You can see several tributaries and alluvial fans feeding the Ganges River. And this view really demonstrates the rain-shadow effect. And what I mean by that is warm, moist air emanating from the Indian Ocean meets the Himalaya, and as that air rises, it drops all of its moisture in the form of precipitation. And so we have green lowlands and very snowy high peaks, but very arid territory over here.
Well, one of the more nice places, or the neat places to take photos from orbit, is the Middle East, because it's always clear, hardly ever a cloud in the sky. And what we're looking at here is the Sinai Peninsula, pretty much in the center of the frame, with Egypt and Africa to the top, and the landform here that we see. We take photos from orbit for many different reasons. A lot of them are taken just due to the sheer beauty. However, we do take a lot to study the Earth. Geology is a major issue, meteorology, how humans are affecting the climate, and how they're using the land. So to give you an example, this slide has a lot of those issues in it. The Dead Sea Fault right here, with the Dead Sea sitting here, is the lowest place in the world, over 300 meters below sea level. Everything flows in there pretty much. Nothing flows out, obviously, at that sea level. It represents the geology that we look for. From space, we can see the big picture of how different plates of the planet are moving around and tearing apart, and we've been studying that in a lot of different areas of the world. Vegetation and how we use the land, the little vegetation streak you see right here separates Egypt to the south from the Gaza Strip. And also, if you look right in this area, is the river Nile Delta, where it's highly cultivated, and the ribbon of the Nile, which is very historic both in religion and history, as it flows or comes from southern Africa there. Again, we can study these areas using color visual photos like this one, or color infrared, which you'll see here in a few moments. And we can understand how the inhabitants are using that land, whether they're overusing it or underusing it, how the irrigation and water system is working. Also, meteorology from this slide. If you look down in the left part here, you can see basically streaks caused by high winds and sand dunes and different materials moving around. Another example of this is Western Africa. Over in here, we wind up seeing a lot of sand and material blowing off the western deserts of Africa in the same systems that bring us the hurricanes across the Atlantic to Central America and to the United States area. We have documented results that show material, maybe off your car in the mornings, of sand and dust that has really come from the African continent and has just been carried in the upper level winds halfway around the world. Another photo here showing the effects of humans on the environment. This is the Okavango River Delta in northern Botswana, which is in the southern tip of Africa. It's an inland delta. It's kind of unique in that the river flows into this delta. Usually we think of deltas being into the ocean like New Orleans, but this is an inland delta. Heavy rains and wetlands in northern in Angola flow down the river and enter the delta at this point, and due to a bunch of faults and rifts, again geology-wise, causes the river to dam up and form this inland delta. The size of the delta is kind of unbelievable. From here to the tip of it down here where it enters the Kalahari Desert is about 95 miles long, and it takes over 6 months from the water to move from this area to maybe the tip of the delta. During that time, it's absorbed, used by the plant life, or evaporated, and some of the civilizations around there are trying to pump water out of this area to mining operations to cities, again, which will destroy this area, which is very similar to the South American rainforest. It is one of the more wilder regions of the African continent. Huge herds of buffalo, elephant, and zebras and other animals roam there quite often. We photograph this area almost every shuttle flight if we can to help document the changes in this delta, because it's kind of a miniature model of how other areas of the world are working. A lot of times in these areas up here we see forests or see fires where people are burning off the wetlands so they can use the area for grazing, since cattle herding and cattle is the biggest industry for the local population. And over the past 100 years, we've documented the changes in this river delta, how different weather phenomenon and how humans are affecting it, and it's slowly shrinking and going away.
This is an oblique view of Lake Chad. Lake Chad is located at the border of Chad, Nigeria, Niger, and Cameroon. It's also a very good subject for photography on each shuttle flights, as it is a very shallow lake, less than 25 feet deep, and that's why the size varies seasonally very much. The picture shows the water on the southern basin. The picture is looking south. So you have the water on the south basin, and you can see also very big dunes covering the eastern and the northern edges of the lake, where water used to stand before. And also can be seen the prevailing wind direction very easily with the agricultural burning blowing to the west. This near vertical false color infrared picture shows a very unique agricultural pattern south of Khartoum between the white and the blue Nile rivers. Of course, it's infrared, that's why everything green looks red on the picture. Hundreds of rectangular fields can be seen over a size of about 100 miles, and also straight lines that are the water field canals irrigating this region. This is by very far the biggest irrigation project in North Africa. In a periodic cycle throughout the year, half of the fields are in crops essentially of cotton, and the other half is fallow for resting soil and also for pest control. This is also an oblique view of the Strait of Gibraltar looking southeast. Mediterranean Sea is on the upper left corner, and you have the Atlantic Ocean on the right. This is Africa on the top and Spain on the left. The sun glint highlights very much the high currents through the strait, and also current shears along those straight lines starting from the coast of Spain. Also, we can see very easily surface waters patterns thanks to the glint, and also some very small ship wakes. The sun glint highlights also the town of Tanger here in Morocco, Africa, and also the Bay of Cadiz in Spain. And also, you can see very long contrails on the bottom of the picture. This is a nice oblique view looking northeast of the whole Alps mountains chain, which is a natural border of binding some of the main European Space Agency countries participating in the International Space Station program. France on the left, Italy on the right, Germany on the upper right corner, and Switzerland in the middle. Can be seen very easily the pattern of the Rhone Valley with the famous curved inverted L shape and a 90 degrees angle here leading to the Geneva Lake. And also, it's very easy to see those big valleys here on the Italian side, as they have been shaped as a U letter by glaciers during the last ice age. This is the Aosta Valley, and this is a valley leading to Turin. And here you see the Isère and Maurienne, where a lot of very famous French and Italian skiing resorts are located.
This is a view of Greenland, and because of the time of day that we launched, we had sunrises usually in the very southern part of our orbit, and then we had sunlit as we ascended in our orbit, and had sunsets at the top of our orbit. So this is kind of a late afternoon shot. And of course, it's easy to pick out all the fjords along the coastlines, which were created during the last great ice age about 10,000 years ago. And it's interesting to find out that the ice, particularly in the center of Greenland, is about 10,000 feet thick, and that there are still rivers of ice that are flowing towards the oceans, where the ice then either melts or forms icebergs. This is a view of volcanic terrain in the central Andes in South America. And I like this view because it's very exotic looking, and if you didn't know you were looking at the Earth, you might think we were exploring another planet. The geologists are interested in pictures like this, not only because of the many different types of volcanic landforms that they can pick out in the picture, but also because there are a lot of dry lake beds, and they can pick out ancient shorelines and some of the alluvial fans. And they can also chart changing water levels in some of the lakes, and there's a very small turquoise lake, if you can see it up here in the upper right.
This near vertical photograph of deforestation in Brazil was one of our Earth OBS targets that we were asked to study, and shows two distinctly different agricultural land use patterns in terms of their maturity. The larger rectangular shapes down on the bottom of the view represent an older and more fully developed agricultural environment, while the smaller, less developed areas are more recent agricultural development. This scene is fairly typical of the landscape in southwestern Brazil, by the way. Photographs such as these are excellent tools to illustrate the areas of change that are occurring in some more remote areas of our world. They provide the scientists with insight into the rate at which these tropical rainforest and the transition zones of the tropical rainforest are being altered, and in some cases, as shown here, in a very dramatic way. This is a photograph that shows the southern part of the Eleuthera Island in the northern Bahamas. Looks like a nice place to visit. As a matter of fact, if you look again in about 20 years, you may see me on a sailboat down there someplace. The hook-shaped island encloses a relatively shallow platform, as evidenced by the lighter blue color, which is surrounded by the dark blue, much deeper water. The feathery pattern in the center here is a platform of sandbars and sand channels created by the tidal currents that are moving in and out and off of the platform. The channels serve as a funnel to move large amounts of limestone off of the platform and down into the deeper water. This, of course, is a fantastic view of the Grand Canyon, created by the Colorado River that starts in Rocky Mountain National Park in Colorado, and then works its way down into Lake Powell right here, created by the Glen Canyon Dam there, and then cuts the Grand Canyon, 227 miles long in total, most of it that you can see in this view, and averages about 10 miles wide and a mile deep. Now, if you've ever visited the Grand Canyon, you probably stood at the village on the rim right there and marveled at how magnificent the site was, looked across to the north rim that is in the Kaibab Plateau that is covered by snow here, and it's just equally a marvelous sight from space. The Mount Ospina Glacier in southern Alaska is a classic example of a Piedmont glacier lying along the foot of a mountain and then flowing into the sea. The principal source of ice for this glacier is provided by the Seward ice field that is up in the northern area here, and then the ice flows in to the glacier through these three channels. The glacier moves and surges, and that moves the earlier formed moraines outward, and in expanding concentric circles, and creates the patterns that you see here as it moves into the ocean.
Going to the other end of the globe, from north to south, we're down here near Antarctica. This is Heard Island, which is down near Antarctica. And the special part of this picture is the wind patterns that you can see in the clouds here. As the wind flows past the island, it creates these vortices called von Karman vortices. As the vortices develop, you can see how the cloud patterns develop and dissipate, causing these opposing vortices in the wind patterns. So not only do we see the wind patterns, but we also see the cloud formations develop there as well.
We were very fortunate to have several crystal clear passes over Japan, and this is the southern end of the island of Kyushu in Japan. And up near the top of the frame, you can see the volcano Sakurajima with a little bit of steam plume emanating from the top. You can also see quite a bit of ash collection near the summit. And also what's striking on every pass over Japan is the population density. And I think you can appreciate in this view several areas of population density, several large cities, including just to the west of Sakurajima, a town called Kagoshima. And it's interesting that the school children there have grown so accustomed to volcanic activity that they often wear hard hats to school.
This is our last picture in our series of slides. This clearly is a mission that was dedicated to looking at the health of our planet, and if there's anything that the entire population of the planet's interested in, it's the health of our home.